Morning, everybody. I'm going to just give a couple of pages of notes today because we have our collaborations. I want to talk about some examples in rotations. So let's think about the effect of mass and bond length on the molecular partition function for rotations. So our quantity of energy that's relevant is this hcb, where B is the rotational constant. Of course, H is Planck's constant, C is the speed of light. So relevant for B, if we look at, well, for this whole thing, hcB is equal to h bar squared over 2 mu r naught squared. And if you calculate that, then that has units of joules. The reduced mass is the mu. And if we think about just diatomics, then this simplifies. So if m1 is equal to m2, then we just have m squared over 2m, or just m over 2. So now let's look at some diatomics. So here I've got oxygen, hydrogen, nitrogen, chlorine. Here are the bond lengths. Here's the reduced masses, which is just their atomic molar mass divided by 2. And then the moment of inertia, if you just plug these numbers in, then in units of AMUs times picometers squared, this is what you get. And this is relevant because the smallest one of these quantities, since this is in the denominator, will give us the largest B. So we get the largest rotational constant for hydrogen and the smallest rotational constant for chlorine. And then oxygen and nitrogen, as you might expect, are somewhere in between. So of these four molecules, which one would we expect to have the largest Q rotation? So if we go back to, in our notes, we talked about Q rotation is KT over sigma HCB, where sigma is our degeneracy, which is going to be 2 for a diatomic. The smallest B will be in the denominator, will give us the largest Q rotation. So that's going to be then chlorine, because chlorine had the largest moment of inertia, so it'll have the smallest B, so it'll have the largest Q rotation. Okay, who cares? Well, it is relevant because now let's think about this question. Which molecule would be most easily excited rotationally? Would you think it would be a light diatomic or a heavy diatomic, or maybe we can't generalize? Well, the PJ is going to be the degeneracy times e to the negative ej over kt.
It's 8 o'clock.
Divided by q. And then the q has this kt hcb, right? So dividing by q basically sends the hcb up here. Okay, so let's then compare the population in the first excited state to the ground state for these two molecules. So HCB for hydrogen, we know is 60.9. For chlorine, 0.244. So just like we said, the chlorine has the smallest B. All right, so put in those numbers, blah, 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 math, math, math. Our degeneracy is here, 2J plus 1. For the first excited state, plug in the numbers. The HCB over KT cancels here, and we end up with 1.67. So as is common with rotations, the first excited state is more populated than the ground state. That's a little different from vibrations, or certainly from electronically. And it's because of that degeneracy for rotations, how high it goes. So anyway, there's 67% more in the first excited state than the ground state for hydrogen. With chlorine, do the same thing, it's even bigger. So you have 3 times as many molecules in the first excited state as you do in the ground state. And that, to me, is counterintuitive. Does this mean it's easier to spin a heavier molecule? Well, yes. Yes, it is. So how do we conceptually understand this? You got to think about the correspondence principle. So as you get to a larger molecule, you're getting closer to a macroscopic system. Now, I'm not saying that chlorine's a macroscopic system. Still nanoscopic. But As you get in that direction, then the energy levels get closer and closer together, closer to a continuum. So it's not so much that it's easier to rotate just because it's heavy. It's because it's heavy, the first excited state isn't that much higher than the ground state. By comparison to hydrogen, the gap is bigger. So that's one way that you can understand why chlorine's easier to excite. All right, that's same thing. Let's take a look at something called the high temperature limit. So when we came up with this expression for Q, we changed a sum into an integral. And I just want to talk about when is that actually valid. So we define something called the rotational temperature where we compare HCB with KT. So HCB is our relevant energy for rotations. That's part of the energy eigenvalue. And then KT is sort of our thermal temperature unit of energy. And I'm going to replace the T with a capital theta, and we'll call that our rotational temperature. So this is just a definition. And solving for the temperature, so theta in this case is temperature of rotation, HCB over K. So this is the temperature at which the energy of rotation is about the same as the thermal energy in the room, so KT. So then the Q rotation, this high temperature limit, would be T divided by sigma theta rotation. And the high temperature limit would be when this ratio is greater than or equal to 10. And that's just really a rule of thumb. That's when you can go from the sum to the integral. So let's solve for this for iodine, plugging in the numbers here, and we get 0.054 Kelvin for our rotational temperature. So the high temperature would be when we're at 10 times that value. So that would be 0.54 Kelvin. And so this is perhaps surprising that we're already at the high temperature limit for half of a Kelvin. So that's a really low temperature that we can use the integral instead of the sum. All right, that's it for today. Get your problem set done, and I'll see you on Monday.